The last thing we talked about were prime and irreducible elements, and let me make clear, whenever I'm talking about these kind of elements, I'm talking about elements that are non-units. The last theorem we had is if R is a domain, any non-zero prime is irreducible. And so we actually went through it for this class. Now, of course, it's very natural to ask about the converse. How about this? That is to say, if you're irreducible, are you necessarily prime? And the answer is no. These notions actually, if you think about non-zero elements, these notions actually, irreducible and prime actually coincide in a unique factorization domain. Which is why the old definition you hear when you're beginning about, oh, a prime integer is one whose only factors are itself and one works. What about in general? Can anybody give an example of something that is irreducible but not prime?
1 plus square root of 5. And
That's kind of an interesting old chestnut, right? I mean, often you'll see this in like a beginning number theory course or beginning algebra course. So if you look at R being this room, which this notation means all complex numbers of the form a plus b radical -5, where a and b are integers. If you look, well, let me pick off some for you. Okay, that's the easy way to do this. And the more exotic way to factor this is that. Now, it turns out that 2 and 3 and these two elements are both irreducible in this ring. But there's stuff to be shown, right? I mean, how do you know that, you know, deep in the depths of some Stephen King novel, there aren't two complex numbers of this form that multiply together and give you 2, for example, or 3. And anybody know how you show that this doesn't happen?
Norms.
Right. The reason this might have shown up in a number theory class is because you were probably looking at norms, which we'll talk about later. And you can actually use norms to show that these are all irreducible. Now, once you believe this is irreducible, 2, for example, is not prime because 2 obviously divides this product. But it doesn't divide either one of these because for it to divide, for example, this, you need 1/2 plus 1/2 radical -5, which is not in here. Right? So there's a standard example, 2, 3. In fact, all 4 of these are examples of irreducibles that are not prime. But I did wave my hands. Here's one that's easier to see, I think. I like this example. Let R equal, take your favorite field. This is sort of like a polynomial ring that somebody did the old Yeller thing to the X term. All right, so this is the set of things that look like A0 plus A2 x squared plus A3 x cubed, AN x n, AI, whatever our field is. So this is the set of all polynomials with this got a 0 linear term. When you add 2 polynomials that are missing the linear term, you get a new polynomial that's missing the linear term. When you multiply 2 polynomials, so this is actually an integral domain, right? Notice that x squared and x cubed are irreducible. And I'm going to appeal to your past algebra knowledge for this. notice the degree of x squared, for example, is 2. So if you were to factor that down, if you're going to factor degree 2 polynomial, you've got two choices. Degree 0 times degree 2. That's one way to do it. But that's not going to help your case because all degree 0 elements come out of the field. And so they're units. Okay, so that doesn't help. Okay, degree 1 times degree 1, no degree 1s. Right? So x squared is irreducible. And there's the same argument for x cubed as well. You can go 0, 3, which again, you've got a unit, or you can go 1, 2. And no matter how you cut that cake, there has to be a degree 1. So again, you can't do it. These are both irreducible elements. And notice that x6 so for example, x squared divides this product, but it can't divide either one of them because that would require the existence of a degree 1, right? And you can do the same thing with x cubed. So these are both irreducibles, not prime. Okay, and there are all kinds of other examples that you can amuse yourself with. They give this kind of effect. Irreducible is much a much larger class than prime or non-zeros. Okay. Now I'm going to do a short foray into multiplicative sets. So it may look like I kind of, sprang my gizzard and lost my mind here, but there's a reason for that because I am going to we're going to come full circle with this, and I am going to give in a factorizations technique, of course, a ideal theoretic characterization of unique factorization domains. Definition. You can actually do this for any commutative ring identity. I'm just going to restrict the domain to make it easier because that's what we're talking about anyway. S and R, a non-empty subset. We say S is multiplicable closed. If ST in S implies ST is in S. So multiplicative closed set, I think, is precisely what you might think it would be. It's just closed under multiplication. Not necessarily addition or anything else, it's closed under multiplication. And S is saturated. By the way, saturated is usually another adjective that is piled upon multiplicatively closed. There's no particular reason why you need to do this, right? You can talk about any set being saturated. If AB is in S, implies A is in S, and well, let me just say A is in S, and that means both A and B are in S. So basically what it means to be saturated is it contains all its divisors. Anything that divides something in the set has to be in the set. So in particular, in our situation, if you have a saturated set, I know one element that has to be in there for sure. Right, one, right, because one divides anything. All right. And multiplicatively closed and saturated is of particular interest. Now, here's one of the big things about the motivation for saturated sets is fractions. And this is the context where you've probably seen this. suppose S and T are elements of some set, right? And you want to make a new ring by creating fractions. Well, the way we add fractions, if we continue in our tradition, says a denominator of ST, right? So, multiplicative sets, one might think of their genesis coming from the fact that you want the set of denominators to be multiplicatively closed. S is the denominator, T is the denominator, you need ST to also be in your collection of denominators, right? But in a certain sense, and the reason that this works so well comes from the following theorem. Let R be a complete identity. Guess I am kind of going to give up a more general, and I an ideal. If S in R is a multiplicable closed set such that S intersect I is empty, then there exists a prime ideal, an ideal P containing I such that P intersect S is empty and P is maximal with respect Let me draw a picture of this for you. Here's what this theorem says. So here is your rather elliptical looking ring. And suppose you have some multiplicable closed set, or I'm sorry, suppose you have an ideal I putting in here somewhere. And suppose that you find a multiplicatively closed set S. And suppose that there's no overlap. There's nothing in S and I. What this says is you can sprinkle a little fertilizer on I and grow it up to some ideal P. But the P also misses the set and is prime. And in fact, the primeness actually comes from the fact that it is maximal with respect to its problem. How many of you have seen this theorem before? Some of you have, some of you haven't. Okay, so let's see why this is true. The first thing is I'm going to build P. Let's let I be our ideal and S multiplicative closed set such that I intersect S is empty. Now, I'm spoiler. I'm going to tell you what my strategy is going to be. I want to build or at least claim the existence of an ideal that is maximal with respect to the property of missing S, right? I itself misses S. I want something that's maximal with respect to property. What does that sound like this is a job for? Very good, right? So let's let whatever that is, like a lambda or something, be the set of J such that J contains I, J is an ideal, and J misses S. Okay, so I'm going to consider this. This is the collection of all ideals containing I that miss S. Notice that And we're gonna partially order this by set theoretic conclusion. So this is gonna be similar. I probably won't go through quite all the details that I did last time. This is very similar to our other Zorn's lemma argument. Notice that I is in gamma, so gamma is not empty, or whatever that letter is. It's not empty. Right. Now, to apply Zorn, I need to show that given any chain in this collection of ideals, there has the upper bound, there's an upper bound that's still in there, the chain. So this is chain, so this is totally ordered subset of this guy. And just as before, we're going to let U equal the union alpha. Notice that U is an ideal as back when we did our earlier Zorn's lemma argument, we went through a little bit of pains to show this, and it was exactly because of the fact this was a chain that that this union turned out to be an ideal, right? Okay, check mark one. U contains I alpha for all alpha. So U is upper bound. So we need to show that, is this thing still in here? Well, what does it take to live in here? It needs to contain I. Got it, because every one of the things in the chain contains I. Needs to be an ideal. Got it. And the final thing is it needs to miss S if X is in U intersect S, then X is in J, that is I alpha, some alpha. Right? Therefore, X is in I alpha intersect S, which is a contradiction. So, by Zorn, so every chain has an upper bound, so by Zorn's lemma, it must be the case that our set has a maximal element. Everybody okay so far? Let's call it P. And in fact, let me point out that there may be many maximal elements, right? The Zorn's limit doesn't say there's just one, just says there is a one. Okay. And the final bit, I claim that this P, which is, remember how it's constructed, this is a maximal element of our set that we constructed here. Once we convince ourselves that P is a prime ideal, we're good to go. So to this end, let A, B, and P, and A, B are elements of R. Suppose A, B, not in P. I'm going to go for a contradiction. Let's suppose that we've got two elements not in P whose product is in P. So notice that notice that the ideal generated by P and A, remember, this is just the PA is just the set of elements of the form little p plus R times A, R is element in the ring, so. Notice that strictly contains P because A is not in there. And so since it strictly contains P, what can I say about it?
It's us.
It must meet S. So there exists R and R, let's say R1 and R, and P1 in P, and S in S1 and S, such that P1 plus R1A is equal to S1. Right, so there must be something in P plus a multiple of A that's S. Also, so we get a similar equation, P2 plus R2B equals S2 in S. I agree with you. Now, let's just see what happens here. Multiply these two equations. P1, P2 plus now notice, and this is just for multiplying out both sides of this equation. This is in S because S is a multiplicatively closed set. This chunk right here is clearly in P, right? Because every term has something coming out of P. And this one is also in P. So we conclude that it's in P and it's in S. If P intersect S is not empty, and there's your contradiction. So P must be contradiction. Questions on that? Let me get this corollary because I've really never been able to resist cool corollaries. Actions, not do that. Let's do the more general thing. If R is a commutative ring of identity, and I in R is an ideal proper, then I is contained in minus one. This is what we proved like last time. How do we get this from this theorem?
Just consider the set of volumes.
Okay. Now I need a multiplicative closed set that misses that. There you go. There is the easiest multiplicatively closed set in the world I can think of. Notice that I intersect S is empty. So there exists a prime ideal P containing I such that P intersect 1 is empty and P is maximal with respect to this property. Well, what does it mean for a prime ideal to be maximal with respect to missing 1? It means it's straight up maximal. It means any ideal that properly contains P must contain one. So P is a true maximal ideal because it's maximal with respect to the property of missing one. Any ideal that properly contains it must contain one. I think it's really neat that we pull off that corollary like that. Okay. So let me give you another. This is kind of the second piece of. There's two big kind of important theorems about multiplicity closed sets, and that's one of them. Here's the next one from a prime ideal point of view. But any questions?
So black two, how do you say that L1, L2, and D is also in B?
Because my assumption was A was not in, A and B were not in P, but A B was.
Oh, okay.
Right, and so since A B is in P, yeah. Okay, other questions? Yes,
Sorry, what do you mean by true? Like, why do you have the true in quotes?
because the P here at the beginning is only maximal with respect to a property. Right,
Oh,
right, that's what I meant by
Thank you.
that. Theorem. One, four, three. Let S be a subset of commutative ring of identity. Then S is saturated and multiplicatively closed. If and only if. Anybody know what the punchline of this is? This is,
This is the.
I'm sorry.
The complement of the union of farm.
Good. If and only if S is the complement of a set theoretic union. This is actually a very important theorem. So if you take a whole union of prime ideals, so for example, in the integers, take the union of the ideal generated by 2 and the ideal generated by 3, right? So this is a union. So it's any integer that is either even or is divisible by 3. If you look at the complement of that, it is a set theoretic union, which comes up in community algebra a lot and is kind of an important thing. So let's prove this theorem. Well, let me tell you what's going first. Saturated. Multiple. And actually, I want to kind of take this apart a little bit. So let's let X be something that's actually in the complement of the saturated and multiplicative closed set. So pick something, anything in the complement of, S, so it's not in the saturated. And look at the ideal generated by X. What can you say about this?
Then a maximum. That's the empty.
Okay, that's the important thing. This intersection has to be empty. Can somebody explain that a little bit better?
The ideal generated by X is in the form X times R, and so if it were an S, that would apply that X is an X.
That is correct. Anything in here is a multiple of X. So if Rx is actually NS, saturated states pick up all the divisors, so it has to pick up X, right? Okay, so now that we've gotten this far, so we know that X and S don't overlap. We know from our previous theorem that we can, get some roids here at old X and grow it up to PX. Prime ideal, maximal, with respect to property that PX intersect S. So basically, we can expand X to this prime ideal that's maximal with respect to this property. So notice that what we're trying to do, remember, is we need to show that SC, the complement of S, is a unit of prime, is a union of prime ideals. So let me first write this. Right. So S complement is the union of all X's, and notice that this is equal to certainly this is contained in this, right? Because every PX contains its respective A. How do we know the other containment? How do we know that this is? Because on the face of it, I'm unioning a much bigger chunk of things here.
None of them make us. So
That is correct. None of these PXs meet S, right? So this thing is certainly contained in SC, which equals this. Everybody cool with that? There you go. Now, how about the other way? Well, for the other direction, we now suppose SC is a union of prime ideals. The first thing I'm going to do is let's suppose we have ST and S. Those S and T are in S. Well, notice that what that means is S and T S and T are not in any of the primes. In the union, that is SC. Right. Therefore, ST is not in any of these primes. Because of course, and it's important here that the idea is prime, because if ST was in one of those primes, then either S or T would have to be, which we've already said can't happen, right? So ST, or I'm sorry, so S is multiplicatively closed. By the way, I like this part of the proof. Let me point out that really right here, we needed the prime. We needed the notion of prime here to show that S is multiplicatively closed. We do not need that so much for saturated. And if ST is in S, let's just suppose that ST is in S, then ST cannot be in any of primes unioning, turn union into a verb, right? Which means, so S and T cannot be in any of the primes. So S and T are in S as well. But notice in this part of the argument, the only thing that I used was it was a union of ideals. Nowhere did I use the prime. So actually, it's the multiplicatively closed that you need there. Okay. Any questions so far? Let me give you a definition to round out your notes, if you will. Definition. R is atomic. If every non-zero non-unit of R is a product of atoms, which is synonymous with irreducibles. What it means to be an atomic ring is every non-zero non-unit is a product of irreducibles. Sometimes irreducibles are called atoms because we mathematicians didn't pay enough in chemistry, pay enough attention in chemistry, and we think that atoms are the smallest things. But anyway, we'll kind of roll with that, won't we? Domains that are non-atomic, for undergraduates, at least in the first course, are a little bit exotic because I think almost every construction you can think of rings when you first start out, you're going to find that they're atomic. That is to say, when you take an element and you start factoring and factoring and factoring, you'll eventually get stuck. You go, I just fooled you because that's not the definition of atomic. That's ACCP, right? But most of the things you can think of are probably ACCP as well. Let me give you the classical definition of a unique factorization domain. And I know, sloppy teacher, I've been throwing this terminology around with it being a little bit undefined, but now I'm going to be formal to tell you what a UFD is. And like I say, this is classic definition. 1, 4, 5. And just for fun, I'm gonna give you, another couple of definitions here. We say the integral domain is a domain. We say R is a unique factorization domain. UFD. If R is atomic. So you need that first. You need to have this property here that every non-zero non-unit is factored into your irreducibles. And given irreducible factorizations, let's say alpha 1, alpha 2 up to alpha n equals beta 1, beta 2 up to beta m, then n equals m. So if two irreducible factorizations, if you write two different irreducible factorizations, they have to be the same length. And two, there exists sigma in Sn such that AI is UI beta sigma I. Or UI a unit in R so this is the classic definition of a UFD. What does it mean to be a UFD? Well, first of all, it's got to be an integral domain. And second of all, it's got to be atomic. Such that given any pair of irreducible factorizations that are equal to each other, you have n equals m. And what is this business with permutations? This just means that if you reorder the betas, you can pair them off up to a unit, right? So this is like, like two ways to factor 12 in the integers, right? And they're rearranged, but if you rearrange this in the same order, then they pair off up to a unit. Right? That's essentially it. Let me make a number of remarks. What if you remove the second condition? Then you actually get a more general type of integral domain where you may not have unique factorization, but any pair has the same length. These are called half factorial domains. We'll talk about those later. Let me give you a couple of equivalent definitions for UFDs, which one of them is a little bit more streamlined. And the definition of UFD, by the way, how many of you have seen this definition of UFD before? Has anybody seen another definition? Yeah, right. There's an ideal theoretical one. This definition is. Yeah, so you can actually recouch this in terms of ideals, right? And prime ideals containing principal ideals, essentially. This definition, I don't even know how old it is, but it's old. Uh. Um. Uh. Such that. Alpha I. U I. Beta sigma I. U I. U R. So. This is a shorter definition. Anybody see what the difference is? It's almost the same one.
They're already the same link.
That's right.
This is what you're talking about.
That's right. So this one here, the classical definition is given any two irreducible factorizations, then N and M are the same and basically graph factorizations. What this one means is to tell us a UFD, all it has to do is be atomic and two irreducible factorizations of the same length are the same. If this holds true, it is impossible to have different length factorizations, which is a little bit surprising. Here is another one.
It's the proof that those are equivalent particularly difficult, or it was proven rather recently.
It's kind of hard, I think. Yeah, and it does very heavily depend on the fact that you're dealing with an integral domain, because you have to interplay the multiplication and the addition, and that's the tough part of it.
Well, this is what you're talking about Wednesday, right? With the addition with the mono generated by 2 and 3, you can have that structure, but no
That's right.
ideal
By-
domain can have that
If
structure.
you believe this theorem, you're exactly right. That's a corollary to that is my example from earlier. It was holds water. Here's another definition that's equivalent. R is a UFD. If and only if, well, so I should be, I mean, I'm talking about domains all the time, but I should be extra careful and make sure I've got this right. R is a UFD if and only if every non-zero prime ideal contains a non-zero prime element. This is an ideal theoretic characterization, and usually this is what makes the UFD property actually more powerful. A lot of the factorization properties we'll deal with, the half factorial property and some of these others, there's not a good known ideal theoretic characterization. However, UFDs are determined by prime ideals. That is to say, if you have any non-zero prime ideal, it must contain a non-zero principal prime ideal. Let me point out that this does not mean that all prime ideals are principal. Because you might have a very big ideal, but it's got some prime elements that may not generate the whole thing, but they're inside there. Right? This is equivalent to the other ones here, and we'll talk about why this is true next time, but this is actually very powerful, and this gives shortcuts to classical results about UFD. Okay, any questions? Any questions? All right, well, we will see you all